Hi everyone, welcome back. I'm excited for this session. I have with me Ole Koch, who's the Product Development Manager for Quantum at Teledyne E2V. He's leading the product development of a range of quantum-enabled products, such as miniature atomic clocks that we heard about earlier, gravity sensors, and satellite payloads. He'll be covering quantum sensing applications within the aerospace and defense industries. And I'd like to welcome Ole. Over to you.
Thank you, Amir, for the kind introduction. Good to be here. I've got a few interesting slides planned for you. Also, thank you for the Quantum Tech team for preparing this nice conference. I'm looking forward to the next few days for a few very interesting talks and discussions and chats. So in my talk, I'll be talking about quantum sensor applications from the aerospace and defense industries and giving you a bit of background on the experience we've gained and the contacts and the knowledge we have, how we do that. But I'll initially just begin for the people who are not too familiar with all the quantum technologies, give a little bit of background. You would have had some background already, but it would always be good to have a slightly different view on the background. Just for quantum-based sensors, so that's what I'm mainly aiming at, is basically sensing technologies on quantums. There's actually a whole range of different technologies underlying these sensors, and they are quite vast differences. So you could begin at vapor cells, and then go to actual diamond into solid states. Then you've got under vacuum cold atoms and trapped ions. And then a lot of activities on actually exploiting the photons. And probably if you think a bit further, there's probably a few other applications out there. So if you know of anything else which I missed, put it in the chat, remind me of that as well. But, and I'll go a bit further. I'll talk a bit about actually quantum-based sensors. There's actually a whole range of sensors out there. And I've provided a little chart of what's actually out there and group them also by size. So for example, let's take the example of atomic clocks. So there you can get millimeter-sized technologies, so a few 10 cubic millimeters or cubic centimeter, so 2 thumbs in size, and these are atomic clocks. There's 2 or 3 available out there. A little advertisement from Teledyne, we do have one available now as well. And then there's a whole range of clocks available at sort of the 10 centimeter scale. And you also have the very large fundamental science defining the second atomic clocks. So for example, cesium fountains or optical atomic clocks, which are in development and at some point in the future will redefine seconds. If you then go to gravity sensors, by my knowledge, I think for quantum-based gravity sensors, there's only the cold atom technology using interferometry. We are developing one of those, and I'll talk a bit more about that later on. If you then go towards acceleration, and the difference between gravity acceleration is mainly on if you point it vertically or horizontally. And then for acceleration, you do have a bit different classes available. Again, the very large, very fundamental high performance systems, but also a bit more compact systems. And I'll talk a bit more about what this picture actually is later on. Then you could go towards rotation sensors, and I found a few examples which go from very small to actually still very compact sizes. But again, you can go to absolutely fundamental science systems there. And then magnetic sensors, what we do also have, you've got very small vapor cell-based technologies, but again, fundamental sciences available. So what do I want to say with this? Actually, quantum sensors is a very diverse field, and there's a lot of things or technologies already out there. Several of these are already on the market, available, and actually there's a whole wave, I'd almost say, coming now of new technologies having just entered or soon to enter the market, really changing things. Just for the people who've not been that much involved in quantum technologies, I'll give a very brief example of actually what's the difference between a classical and a quantum technology sensors on the example of an atomic clock. So let's say the classical atomic clock, the wristwatch, but actually the more sophisticated crystal oscillators are literally mechanical, very, very well manufactured devices, which oscillate at a certain frequency. And that depends on how well your manufacturing control is on what frequencies actually oscillates at. Whereas atomic clocks, the biggest difference is, or quantum-based devices, is your reference is not actually something you've manufactured, but it's atoms. So how well can you probe in the real world effects on the atom, read out a frequency, atomic transition, spin change, or whatever. And that is then the measurement device. And you then design these devices very clever so that your atom is sensitive to the thing you want to measure. So for atomic clock, it's a frequency you want. If it's a magnetic sensor, you choose an atomic transition, which has an effect on the magnetic field, and voila, you have a magnetic sensor. So in summary, the big differences are classical devices, it's all about manufacturing tolerances. How well can you manufacture these? And for quantum sensors or atomic clocks, it's just about how well can you actually read out the atoms, but also the added complexity, how well can you shield them from the environment you want to measure in. So a very brief background on the company, I'm actually from what we're doing, and give a little bit of insight why we are actually going into quantum technologies. So Teledyne, I don't know how many people know it, but it's a fairly large company, over 10,000 people now. And we are part of Teledyne Imaging. And I don't always describe us as, if it's technologically challenging and if there's a niche market we can go into, we will usually be there. And try to occupy that market. So we go from machine vision, life sciences, cancer therapy. We have quite a large activity in space. So for example, we have been to every planet in the solar system, including Pluto. I still call it as a planet. And otherwise, we've got underwater submarines, there's semiconductors, we've got several MEMS factories in the company. So actually a very broad range of technologies we have available. And actually, it's all about understanding the technology, having the right skill sets, and the core basis to bring those into market. So now honing in a little bit more on quantum technologies. So we at Teledyne E2V are investing in a new platform technology on quantum, and the specific things I'm developing with my team at E2V is, for one, quantum sensors, so gravity gradient sensors to actually see things in the ground. Then timing, atomic clocks. We're developing a range of atomic clocks, for example, for GNSS or GPS holder activities. And then what we're also doing is bringing these technologies to space. So there's a lot of activity to actually go into aerospace and space and utilize the advantages of quantum for atomic clocks, gravity measurements, acceleration measurements, and so on. And what we're doing is combining our technology heritage and knowledge for space sensors. We have vacuum system manufacturing lines and so on, and combining all of those into really bringing quantum technologies closer to space. And we do also have a little bit of side activity for quantum key distribution for ultra secure communication networks. And I want to talk a little bit more about how we actually do these technology developments, because quantum technologies is actually a very difficult, very challenging, especially want to be at the forefront of technology. How do you as a company really stay at the forefront and make sure you've got the best technology available in your company? And what we are doing, really also fueled by the UK Quantum Technologies program, is a very collaborative approach. So we're collaborating with lots of people. So here I've got a selection of the key collaborators we're working with. So for one, we are partnering with universities, especially University and National Physical Laboratory. We're partnering very closely with to be at the forefront of technology, what they're developing, investigating, and we're following shortly behind them and translating these technologies, but also in a very open, active dialogue that we are aligning our research interests between ourselves. And then we've got a huge supply chain, end user and others on board on a variety of projects in which we are developing all the different technologies we're developing. And so as for the company, something actually very new to do it in this drastic, very proactive fashion, because usually you would have suppliers, let's say, you bring them on board, whereas nowadays we are from day one collaborating with them in a much more open, interactive, collaborative way, which of course means you need to be more open in how much information you share, but the huge benefit is basically the interactions you get with the suppliers, and they actually are really developing with you technology bases, which you can then build into your system, and you know how you have a supply chain evolving. And of course, what we then afterwards bring to the table along this journey is really translating the great ideas academics have into real products. And I'll give you a few examples of the journey later on about this. So to talk a bit about the applications. So in the next following 20 minutes, I'll give you 4 examples, which I think are quite interesting to see where quantum technology-based sensors can really help the future journey of the next generation of devices. For one is looking at GNSS systems. So what happens if GNSS is denied? How can navigation or communication still work there? And then actually have, if you don't have GPS systems available, what can you do? How can you still navigate then? Think of the example of a submarine. They don't have any GPS available. And then is how can we bring quantum sensors into space? And then ground-based void detection. So how can we actually see things in the ground which you currently cannot see? So for one, just a little bit of background about global navigation satellite systems, GPS, Galileo, or similar. I'm pretty sure everyone's familiar with those. I mean, those are amazing systems. And if you would have asked me 20 years ago that I'll be walking around at my wristwatch, probably soon my headphones, my phone, they will all be GPS enabled or GNSS and just constantly know where they are. Not quite sure if I would have believed you, but nowadays the technology has really advanced quite far. And it's an absolutely amazing build system. You can get 10, maybe even sometimes up to 1 meter positional accuracy. But the big problem is it's a too good system, actually. If you look at it, it's so readily available. Everybody's using it. And why should we not rely on it? But actually, what happens if these systems are not available anymore? So what happens if they fail, for example, due to a large solar storm? What happens if they're jammed, spoofed, or if you're underwater, or actually in very dense urban environments, then these signals might go away. I had actually a bit of a look online to look at, okay, how much would it actually cost to jam GPS? And you can literally find them off the shelf, 80 pounds, even found some for 40 pounds. And voila, you suddenly have enough 1 mile, 2 mile radius GPS systems jammed. So you can imagine that people might actually buy these things, car thieves, for example, and suddenly a few miles of a city are GPS jammed. So the question is then, for the people who are actually using this, how critical am I actually dependent on this? Do I need GPS, or will my services also survive without it? So if I'm a pedestrian walking on the street, it's probably not too bad. I'll survive without GPS, without my map telling me. I just need to look at the old school maps. If you're an autonomous car, will you land on a tree, like I'm suggesting there? Probably not. Usually you have good cameras. But let's go towards autonomous shipping now. And I just took the latest example of an evergreen ship. Okay, that wasn't actually due to a GPS failure, but just imagine you're autonomously in the future, you have autonomous shipping, and you have these ships, and you eventually actually go to having limited to 0 personnel on some ships. Then what if GPS fails? Let's say it's a foggy, cloudy night or so again, you could actually have a problem. So that's something people need to keep in mind. So looking at the mitigations, what we can do, and there's quite a few things you can do in case GPS is not available or is jammed. And for one, is depending on what you need from GPS. So if you need the timing signal from GPS, if you're running a timing service, let's say data networks or similar, then what you can do is use atomic clocks to keep it going. So based on an article which is linked here. People have done actually just plotted out versus size, all the atomic clocks available. And you can see there's actually quite a lot of them available, but these range from very different requirements. So you can see on the top left-hand side, the low power versions. So that's where really powers everything for these atomic clocks. And it doesn't matter what your requirements are for the timing. The first and foremost is you need to have low power applications. So think of underwater seismic sensors, which I'm aware of, a lot of these clocks go into. But otherwise, think of the soldier in the battlefield. What happens if they are out there and they want to have communications and other services going in a GPS denied environment? Because you can imagine any somewhat smart adversary will have GPS jamming sort of as part of the arsenal usually available. And suddenly these soldiers might need some local timings. So that's the low power clocks available. And then there's, following that paper, I do agree with that classification as a tactical. So things you would take out into the field, let's say in your base stations, in your tanks, in your vehicles, on drones or similar. So areas where you have a bit more power available and you then utilize these systems. And you can see also there, that's the the miniature atomic clock we are developing. So that's the market niche we are aiming or developing at. So hold this space within the next 1 or 2 years for products becoming available. And then the other one, which I'm not going into much detail, is almost the strategic area. That's where you actually have the clocks who are driving GPS and so on. So very specialized, very high value, large sometimes applications. So now let's assume we have an atomic clock in our system. What good does it do us? If you think about GNSS, for one, it just acts as a local flywheel. So we have acquired GPS and we can just keep going. And now it depends on your mission parameters. What do you actually need your timing for? Is it for communication? Is it for other services, synchronization or similar? And depending on those parameters, and you will need to choose your clock, and then you can either have a few hours, minutes, or even several days of operation without GPS being available. But what you also do get is faster requisition. So let's imagine you're a round cylindrical object flying at very fast speeds over land to a certain destination. And then if you go through a region where GPS is jammed, afterwards, after you've been through that, you can actually have the ability to reacquire the GPS signal much, much better if you have a performance level clock on board. And just basically to say how dominant it actually is, I just looked up a few articles and you could just see, I mean, thousands of GNSS jamming instances are reported for 2020. And people, yeah, so someone had a pig farm and for whatever reason, they didn't want to have GPS available. Vehicle thefts, people, if they basically can crack a BMW or Bentley or so on, have very high-tech gangs, and they will usually just have GPS shows available. Voila, suddenly a few 100 meters or even miles maybe around this, GPS is not available anymore. So this is sort of the simple thing. This is just putting noise out there and jamming GPS. That's simple. But now let's get one step further and actually go towards spoofing. This is where you actually need to be a bit clever and really take the signal, infiltrate the signal, I'd say, and then send out a fake signal, which the receiver will pick up. And I had a bit of a look online to see how far they've actually gotten. And in the public space, I'm pretty sure defense agencies have their own programs who can absolutely do this. But in the public space, and I said the hacker space, you can see people have done proof of principles just with $250 worth of equipment. And you have built your own GPS spoofer, and then you can direct the signals wherever you want. And I believe the picture you can see on the right-hand side is the drone which was shot down by Iran. I believe that was partially due to the GPS signal being spoofed, but do correct me if I'm wrong in the comment section. Yeah, so what can you do? So I had a bit of a read up, and there's a lot of potential algorithms you can use. And there's then basically a head-to-head race with the people spoofing you, how well they can mask the signal. Is it just a brute force simple attack? We send our own GPS signal, more powerful, and the receiver will pick it up. So then the receiver can potentially have an algorithm inside which could just detect that. But also if you have an atomic clock on board, because usually the timing will then drift off, and then you can detect if it drifts off on certain parameters, and then you know alarm bells go off, you have been spoofed. And yeah, the reference on this side, all your GPS are belong to us. You can, that sort of shows when I was computer gaming, some people might get that reference. I'll leave it at that. But that's the reason why I chose this specific reference. So yeah, one other quick example is on data timing, telecoms. I've seen some beautiful pictures, which I just couldn't find for this report, for the presentation now, I'll keep looking, is data centers. There's beautiful pictures of the top of data centers with antennas on top. And these are all the different GPS antennas of the different providers in this data center. So you can just see how much timing need there is for communication data services. And if you look at mobile networks, we currently are on 4G, rolling out 5G, and you think about 6G in the future. And each of these gets stricter timing requirements. So GPS still works, but what happens if GPS fails? Will your entire data infrastructure network go down? Again, atomic clocks, choose the right one. Well, here, if you have a better clock, what does this mean? Mainly, the youth will be able to send more high-resolution TikTok videos. So very good use of quantum technologies. But going back to the defense world, secure communication. So my understanding is one way you can have secure communication is frequency hopping. So where you and the other parties have an agreed pattern to hop the frequencies. Of course, if you don't have a common timing reference, that can be difficult. So that's why, for example, on the soldier in the future, potentially having very chip-scale atomic clocks on tanks and other devices in your mission theater, have these clocks on board. Of course, the better clocks you have, the longer you can stay synchronized with your host. So now moving on to gravity-aided navigation. So this we're looking at the activity if you don't have DNS available or if it fails for a notable amount of time. And we think there's a fairly notable potential market there, absolutely not available at the moment, but just think about autonomous shipping, drones. If things go more and more autonomous, you need to evaluate the parameters of your activity to say how much can it actually survive without GPS. If you're a car, you're probably fine because you have cameras seeing the road and you can deal with that. If you're a ship, maybe, maybe not, depends on what systems you have. If you're a drone or autonomous airplane and you're in the fog, so you don't have any visual reference, then you might want to actually have alternative systems available. So how does it actually work? What's the idea for this? And you can imagine it, you have Earth. Earth is a gravity signature, basically. There's a whole lot of terrain, and there's it's a map of Earth, of gravity on Earth. And this map can actually tell you not exactly where you are, but if you have mapped it, and if you go along a specific trajectory, and you have a good understanding where you've begun on, you can follow this trajectory and match your gravity signal you're getting to your location. So this will not give you GPS style position accuracy, but one important thing, you do not drift with this. So you will always be in that position accuracy. I'll give you some numbers later on that. So I'll talk a bit more about this to actually give you a bit of background into this. So that's actually a study we had funded by ESA, looking into how could you use cold atom-based gravity gradiometers. And gradiometer, for one that specific reason, is if you're on the move, if you're in a vehicle, you will have vibrations, and gradiometers, for one, can cancel out the vibrations. But also, I'll try that later on, the gradient signal has more information in it. And what we're doing, we fuse this with a classical INS system. And then, yeah, so we have gravity gradient maps available. So the SRTM and the EGM 2008. So the SRTM is basically on top of the EGM 2008 maps. And we've compiled our usable gravity map and are now running a simulation. And what are we doing? We're evaluating the feasibility and performance of the system, a number of use cases. So we just went around to say, okay, what can you actually achieve with this? So I'll give you a little bit of an example now. So this is Uluru in Australia, the rock. So what you can see here, this little red dot, I believe, is the actual famous rock. What we've done is on the left-hand side is the gravity map available, and on the right-hand side is then the calculated gravity gradient map. And I already shows you a little bit that actually the feature richness is a little bit better along here. So you can imagine if you go along a trajectory of this, you have more features available along which you can actually detect what you're doing or where you are. So how did we actually do this? Well, basically, initially, we developed a gravity gradient simulator, Gravitas, so where we can simulate quantum-based technology on there and actually convert the gravity signal into the quantum world and then tell us what type of quantum sensor would actually give us what type of performance. And initially, we've done that using basically a perfect sensor, and just to make sure that all the map matching algorithms and so on actually work. So we've run the simulation with an INS system to actually show us that. And then we've begun bit by bit introducing noise. So we firstly tuned up the sharpness of the sensor and looked at the effects of what this produces on the gravity gradient. And then we began optimizing the parameter set based on real life systems, how they would be available, and the ones we're developing to see what type of systems one could build actually would give us the best signal. And then we've run the simulation several times to see the best parameter set. How do you actually condition in classical INS systems with gravity map matching data? And as we went further along, we've added more and more noise sources. So for example, if you're in an airplane and if you bank it slightly up to a certain degree, or if you're driving in a vehicle, the vibrations of that, how they would actually feed into the sensor. And what we've done is then, for this example I'm giving here is the University of Liverpool have run the simulation, and then we're literally just flying around the rock in circles and seeing what it can do. So at 1,000 kilometers height, and you can see the blue line is how the INS would be, and you can see it goes down to 500 meters things. And then if we apply the gravity map matching, you can see we can reduce that limitation down to just above or below 200 meters. Of course, this is a very kind operation for the map matching, because you run around in circles. So what we not yet published is actually if you go to longer times, longer trajectories, how does the drift affect you? What drift can you actually achieve from that? Just as an intermediate conclusion on gravity map matching specifically, it works. So quantum-based gravity map matching works. It gives you better performance. On the specific case as shown, you get around 200 meters. Of course, if you go for longer mission durations and longer, less favorable for the INS trajectories potentially, or just slow drifts, you can actually get significantly better when the GNS system drifts away quite significantly. But the key thing is also the current quantum technology, you need to really be fairly close to state of the art. And depends on the vehicle you're in. Let's say if you're a drone or a very fast flying object, let's say that's quite critical, because the faster you fly, the faster the repetition rate is. And with quantum sensor, repetition rate and sensitivity do scale quadratically. So you need to but be very careful there what you can actually achieve. But if you're in a very slow moving object, let's say a ship or a submarine, these numbers come out quite favorable for you. But a few other takeaways is the gravity maps as they are at the moment, especially this modification on ground, quite good, works quite well. But if you're in the sea, the maps might not be sufficient yet. So you might need to actually invest in better maps. And then, of course, it depends on the use case, how you optimize your parameter set. So moving on a bit quicker now for space. For space, what we've been doing as well is building on our heritage and combining the technologies we have for space technologies. So Caspar is one of the first things we did. This was collateral space payload. This was literally cool atoms, but we sent it through the whole difficult shake, rattle, and roll cycle, the most difficult one you can find, and to see, does this technology basis actually survive? And it's basically the sensor itself. It doesn't measure anything yet, but it was a technology demonstrator. So we should shake it, rattled, rolled it. Certain bits were radiation bombarded. And with one very, very small exception, all of these systems survived, and we were able to autonomously generate cold atoms. Of course, that's just the beginning of the journey. So where's the journey going? For one stepping stone we are investigating now is what is the simplest thing you can measure where quantum centers actually give an advantage. And one we're investigating at the moment is to use quantum-based accelerometers to measure atmospheric drag. And there's two studies we are currently in a phase 0 at. One is ESA, one is UK Space Agency funded. And what are we doing actually here is looking at about 200 to 400 kilometer altitude and measuring the atmospheric drag, because actually up there, it is not that well known and not consistently mapped the atmospheric density. So why are we doing that? For one, there's clear that there's lots of temperature variations, lots of variations in the thermosphere. And for basically just know more and more satellites up there, space debris, it gets quite crowded up there, and you want to predict the orbits fairly well, actually. But these variations do give you certain limitations. And yeah, the drag at these low Earth orbits is quite the dominating source. So with our sensor, we're proposing to go up there as the first mission to actually chart out these areas and give the people running the satellite trajectories much better prediction models available. And here's a few examples of the designs we're currently developing, how we could actually build these sensors into space. So at the top here, you can see the slightly larger mission, which is actually on the TAS SkimSat. So with a little bit more space available, we can go a little bit larger. We can actually have a 2-axis accelerometer. Or at the bottom is the 1-axis accelerometer we're proposing. And there we're initially partnering with Aerospace, who are providing the atom chip and developing certain points for laser, but also in parallel with the University of Birmingham, who are developing novel laser concepts, how to really simplify and shrink down the laser technology for space. So yeah, conclusions on that one, intermediary conclusions. So when the vision is, we want to have almost a fleet of these sensors in space to constantly monitor the atmospheric drag, so the constellation up there, and to really get live data that can be fed into the atmospheric models. But of course, the bigger vision here is quantum-based sensors in space are up there, and they can offer huge benefits. For example, next generation gravity mission could potentially improve these things. Atomic clocks, there's a whole range of applications for atomic clocks. You could put them towards deep space navigation, or in the next generation GPS systems, you could have master clocks in space, which are actually not affected by Earth. Earth is actually quite affecting atomic clocks at the levels they're reaching now, and also several fundamental science missions. But how we see ourselves is that we are not the ones developing the science, but we're the ones who are building the technology building blocks. We know space, we know technology to actually get these things out there. But there's a lot of other people who are also doing this. I mean, on the ISS, JPL sent out the first cool atoms. The Germans are sounding rockets, and the Chinese have also sent a clock up there. But we are the ones aiming at a proper autonomous satellite. And with this one coming to my last slide, so now going back to Earth. So what else can we actually use the gravity gradient sensors for? And for one is actually looking into the ground. And it's quite interesting if you look at, ask people, okay, what's in the ground? And the technologies, what they use nowadays still is actually drill down there and look into what is there. And there's a few other like seismic and classical gravity sensors, which do these, but actually there's a fairly limited area. And if you go, let's say 10 meters down and you've got a 2-meter mine shaft, you cannot detect that at the moment. So what we are developing is quantum technology-based gravity sensors. And with these ones, when they've reached their full potential, you can actually go look into the ground and beat the current classical sensors available. And we're working with, again, a fairly large collaboration there to build these devices. And then what we use this for one is civil engineering. So just imagine under London, where you can look into there. Actually, it's not that well known, but actually also for defense applications. Just imagine you're at the border, you can actually see, are the tunnels down there? Or is there a bunker beneath you? Or is someone trying to dig a tunnel into your base? So all of these technologies, you can be using quantum ground sensors to detect density variations in the ground. And what we're specifically doing is using gradient sensors so that you've really fine-tuned it to be within, let's say, up to 10 meters sensitivity, very sensitive. And with that, I'm coming to my last slide. So just to recap and give you a bit more of an outlook. So for one, quantum sensors are already out there a lot. I mean, just take atomic clocks, they are already everywhere. You can already buy magnetic sensors in widespread use. But actually, it depends on which market you look. There's always areas where there's sometimes even a large part of the market where if you had a better device, it's not served yet. And I think what you're seeing sort of, and you'll be seeing over the next few days as well at other conferences, there's a whole range of quantum technology-based sensors which are or will be outperforming the classical systems now already or in the very near term. And these are now being assessed in real-world applications. So you can really see a wave of the next generation of sensors outperforming the existing classical devices. And a whole range of other new opportunities of areas will also be coming into play there. And with that, I thank you for the attention, and I've seen Amit.
Wonderful.
Live. Yes.
Thank you, Ole. Fascinating presentation. There's so many near-term applications. A question: what timescales should we realistically expect for regular deployment of these non-GNSS devices in military commercial applications?
That probably depends on what technology you use. Atomic clocks, they're available. They're out there, they're in widespread use. It's for filling certain niche applications. So for example, if you go to even smaller ones, what we're aiming at is sort of a little bit of a gap in between there. So those ones you can expect probably in the 1 or 2 year timeframes when a few of the newer ones will be coming out. For gravity map navigation, I think we're basically at the point where we've shown it can happen. It actually brings an advantage. In certain scenarios, the parameters actually match. Let's say a submarine, you have power, you have space, it's a very steady environment and you're not that fast. So you tick all the boxes. So there we don't need to actually build the sensors and get the first trials. So I'd probably guess in the next 2 to 5 years, you can see the first trials happening. And then on the 5-year scale, these things being commercially available. Mm-hmm. And then in space, yes, I mean, the first ones have already flown up. For our space missions, what we're looking at is probably in the 1 to 2 year time scale to really begin the developments, to really get a mission funded, fully funded. And then you're looking at 2 to 4 years to sending these devices up there on autonomous satellites.
And what do you think are the key factors preventing the wider commercial adoption of some of the atomic clocks that you mentioned earlier?
What's the key factor? I mean, for one, technologies are always evolving. So you need to have the next generation technology available. And then people need to actually want to use these and have the right use cases available for them. So that's what we're doing with a lot of market analysis to see which people will actually take them up. Because interestingly, a lot of people are not that well educated or know actually atomic clocks, what they do and what they need it for. So that's a lot of activity we're doing, and probably other timing manufacturers, probably even more so, is to really educate people, because there's a certain group of people who absolutely know what they need and what the systems are vulnerable for. But actually, there's a whole range of other people who aren't actually aware that there might be a vulnerability in their system. Sort of what I heard is the Navy, on certain ships, there's 10, 15 GPS receivers, and nobody quite knows what happens if GPS fails. So I think it's educating the people for one, that's another one. And of course, the better technology that you have, the more opportunities you can make available.
And ultra wideband is also being looked for positioning purposes. How does it compare with quantum sensors?
Could you explain a bit more what you mean by ultra wideband?
It's a question that's come in from the audience. We can move on from that. Or some people talk about vapor cells as an alternative quantum sensor platform for some of these applications. Do you know some of the pros and cons there?
Yeah, I wouldn't say that it's an alternative. It's just part of the quantum. It just depends on what parameters you are. So the clock we're developing is a vapor cell-based atomic clock. And vapor cells, the big advantage is it can be very small. I mean, the chip scale atomic clocks, 2 thumbs in size, are vapor cell-based technologies. That's sort of the minimum you can shrink it down to at the moment. So they are easy to understand, cheaper, better mass manufactured. But of course, if your atoms are in a vapor cell, you lose the advantage of the cold atoms where you're in a vacuum, because you have collisions, either with buffer gas or with the wall around you. So the ultimate sensitivity is limited to a certain level, whereas if you're in a vacuum, fundamental science is still pushing very hard to push these things forward. But then again, these are more complex, larger devices, so it depends on the use case. If you want to have something smaller than a liter, at the moment, quantum technologies will not get you there. In 5 years' time, there's a lot of interesting concepts, how you can really shrink these lasers down and everything else. I wouldn't be surprised if they're also getting there.
Excellent. Okay, with that, we'll conclude. Ole will look forward to seeing what's coming down the line with some of these products and some of the collaborations that you're doing. So again, thank you very much for joining us and for that great presentation.
Yeah. Thank you for listening in. Otherwise, look me up on LinkedIn if you've got any more follow-on questions, or I'm here on the portal as well. Thank you.